If you are there, hello, I cannot hear you actually. Okay, there we go. CJ, are you there? Let's check my microphone. Hold on.
Hi, Mr. Dennis.
All right, there you go. How are you?
Hello.
Hello, can you hear me? Hello. Hold on. Hi,
Hello.
can you hear me? Hold on, let me check my
Yes.
settings. All right, good. All right then. So what are we doing today?
More 5.2.
Right, 5.2. So we're gonna go back to the circuits now.
Wait. Actually,
All right,
could
go
I
ahead.
review 5.1
5.1. All
because
right.
like there's this like triangle stuff that I'm confused with.
Okay, go ahead. Can you show me the triangle thing?
No, like that concept in general, like the what's it where you
Oh,
have to
right,
like
right, right,
find
right.
cosine,
Mm-hmm.
like all that. Yeah.
Hold on, let me try to recall that real quick. All right. So, let me just check the previous Jamboard. Conservation. Okay, let me see the other Jamboard as well. Okay, you are referring to electric charges, right? Static electricity.
Yeah.
Okay.
Yeah.
All right. The triangle thing. Okay. So, all right, I got that. So this is what we'll go through. Okay. So first of all, again, here's the Jamboard. Here's today's Jamboard. Let me just share that with you. Okay.
Hmm.
So, um, anyway, I'm sharing my screen on the Jamboard as well. Anyway, all right. So,
Yes.
again, so what do we have here? So we start off with charges. Okay.
Wait, are you drawing something right? Okay, yeah.
There
Sorry.
we go. Charges. Okay. And then
Yeah.
from charges, the charges will always have, they will have electric fields. Electric fields. Okay. Um, and then from the, they will also be exerting, um, potential difference. But I think potential difference will be later. Yeah, potential difference first. Yeah.
Hmm.
Okay. Okay. So again, what do we know about charges? Let's just summarize this. Charges have occur in plus or minus, positive and negative, right? And
Hmm.
and what we can write here that like charges attract repel, and unlike charges attract. Okay. All right. Now, just like that. Okay. Now, electric fields. How do you draw these? So, to draw electric fields, you will always need a test charge. So use a small positive test charge. Okay. When you use that small positive test charge, you need to see how it moves around around another charge or an electric field. Okay. Moves in the presence of an electric field. Okay, so this is the key idea. This electric field will always be coming from another charge or set of charges. Okay, so let's put that there and leave it here for electric fields. For positive charges, how will these look like? Let me do that again. Okay, so for positive charges, they will always radiate out of the charge. So if this was a positive charge, it will always do that. Okay, away from the charge. Okay, if you have a negative charge, what do you get? You get an electric field that's coming into the charge. Okay, so if this were negative, let's do that again. Negative, the electric field lines come in like so. Okay, and then the for potential difference, we'll put that on next page. Okay, the one more thing about electric charges is that okay, electric charges, electric fields, the closer the lines are to each other, the stronger the magnetic field. Or electric field, right? You say magnetic. Electric field. Okay?
Wait, one quick question.
Go ahead.
EMF stands for electromagnetic field.
No, EMF actually stands for electromotive force. So
Okay,
here,
but it's just voltage.
yeah, that's just voltage. So in this case, the charges, the symbol would be Q. And then for electric fields, the symbol here would be E. Okay? Potential difference, the symbol would be V. But we'll get, okay, so we'll get there on the next page. Okay? So potential difference.
So electric fields are.
Go ahead.
V or E?
E.
Oh, E. And potential difference is V.
Yeah.
Along with EMF. Okay.
Also with that's potential difference in EMF. Okay. So let's just do that right there like that. Okay.
Wait.
Go ahead.
Sorry, another question.
Go ahead.
So positive, its direction is always outwards.
Always outwards.
And electron, it's always inwards.
Any negative charge, the electric field will always be inwards. Okay.
Okay.
Always in.
Wait, but what if it was another electron? If it was two electrons?
All right. So actually, I was waiting for you to ask that.
Oh.
Okay. Outwards, right? So the idea here is when you have two or more charges, those okay, I'll put it on the next page. So outward, right? Okay. So for electric charges or electric fields, okay. Okay, these will combine in a vector manner. Okay. Now what does that mean? In a vector manner. Okay. This means that if you have, it's actually going to be easy now to demonstrate it first with some sort of electric field. Okay. So the idea here is example 1. if you have a if you have this electric field, I'm going to use different colors here now. If you have this initial electric field looking like that, okay, and let's say that this electric field has a, we won't put the unit, let's just put a number. This is 10, right? Okay, and then if you have a
Mhm.
second electric field, let's say going also going in the same direction like this, but it's denser, it's more powerful. So
Mm.
how do you say more powerful as in a drawing? You keep those lines closer together, right?
Right.
Okay, 2, 3. So let's say that this new field has a strength of 30. Okay, this is equivalent to
Mhm.
saying you have an electric field that's really, really dense and in the same direction like this. Okay, and this would be 40. So in other words, electric fields, they just add up really like in a vector manner like this. Okay, so
Mm.
similarly, I'll just make it easier. What if your electric field going this way is 10 and you have an electric field going this way? Let's use a different color. Okay, you have an electric field going the other way and this is 5. So this will give you a result of an electric field going to the right, but the strength is only 5. Okay, so E equals that, E equals that. So the new E is that. Okay. Now, so what would happen if you now have your charges as per your original question, right? So if you have the idea here is this was positive, and let's draw a negatively charged particle here. Let's say that they have equal charges aside from being negative. So this is Q, and this is also Q, right?
Mhm.
So so for the positive charge, we'll follow the original electric field distribution first, like that, right?
Mhm.
Okay, and last one. Okay, so similarly, we'll do the same thing with the electric field here going in this time, right?
Mhm.
Okay, now how do you add them? Again, you add them like vectors. So you would see here that these two are adding up because they're in line, right? So I'm going to draw a new field line here and I'm going to use blue. Okay, so the new field line is going to look like that.
Oh, is that why they attract each other? Because they're both going this. Okay, one's pulling it closer, and the other
Mm-hmm.
is like choosing to go that way.
Yeah. So we
Okay.
can explain this further with by looking at the electric field lines. Okay. So this is gonna look
Mhm.
like that. It's gonna curve in like that. This is gonna, I'm just gonna draw it in between further, but that's gonna stay like that. And then this is gonna curve a little bit, curve a little bit, curve a little bit, curve a little bit like that. Okay. So same thing. This kind of curves, and this kind of curves, this kind of curves, and this goes out, this goes out, right? So, where do you have a stronger electric field? In the middle or here?
Mm, in the middle.
In the middle, right? So the stronger electric field is gonna make those two charges attract each other in the middle, okay? Because if you think about it, the stronger the field lines there, the big the closer the lines are to each other. And when you have close lines, that means that the force is bigger because the electric field is also bigger. But if you so basically we have a strong force here, strong field. I'll use a different color. Hold on. Okay, so this is a strong field here, and we have kind of like weaker field out here, right? Weaker field, and here as well, weaker field. Now, the combination of which is going to attract the um, positive and negative charges together. Okay, All right. So what would happen if you have two positive charges? So if we follow the same rule, I'm just gonna go straight now. If we have two positive charges, I'm not gonna draw the individual field lines anymore. I'm just gonna draw it the overall one together, like that. Huh? Like that. Okay. Because of this, you will notice that here the field is weak, right? So weak
Mhm.
field, and these are stronger fields, right? So because of that, because of this difference in the field strength, um, the strong field's gonna win over. And which way is the strong field basically going? The strong field's making it go that way, to the right, and in this case to the
Mhm.
left here, right?
Mhm.
So that's one way for you to think about the direction of motion for fields.
But what about the electrons? Like if
Okay.
there's two
Uh-huh.
negatives.
All right. So we have two negatives. Let's draw that. So two negatives. So the field's gonna look similar, but instead of pointing outwards, it's gonna point inwards. All right. Still gonna point inwards, right?
Mhm.
Okay. So
Yeah.
um, in, 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 in. They're still gonna repel for the same reason. This is a weak field here. This is a strong field here. So which way is it?
How does it
So
repel?
um,
How does it repel if it pulls it in?
what happens here basically is it's not gonna pull it in, even though the field lines are like pulling each other in. What happens here is because oh, here's another way of thinking about it. The reason it's weak here, and I think this is a more intuitive way of saying it. Okay, so the reason that why it's weak here is because all of these field lines are repelling each other, right? And there's nothing to repel the
Mhm.
field lines here or attract them for that matter. So what's gonna happen here?
Mhm.
These field lines repelling each other here in the middle are gonna just that's they're just gonna keep pushing each other farther and farther apart. So that's what's gonna move. Oops, that's what's gonna move the electric charges here. Okay, so
Mhm.
still gonna be like that. All right. Again, I think an easier way for you to think about this is you have to kind of look at it from very far away, from very far away. Okay.
Mhm.
For you to kind of understand this better. If these charges were, it doesn't matter if this is positive or negative, but very far away, basically the lines look like this: 3, 4, and then uh, getting more and more spread out, right? So even though the field in the middle is weak, even though this is weak, right there, right? Oops, I'll change color again. Okay. So even though this section, the field is weak, so weak field, right? Here you can see that these portions are pretty bunched up lines, right?
Mhm.
But here these are more or less stable. So because of that, stable. So because of this, think about it this way: these bunched up lines are going to try to push each other away so they achieve some sort of balance. So the way to do that is for the electric charges to move apart.
Okay, so you like for it to attract, like you push away
You push away the field lines
the
from each
one it's
other.
repelling.
Yeah,
Okay.
I think this is a better explanation here. Okay,
It's
so
like when you like negatively charge a balloon and you like stick it to a wall.
mhm.
Or is it it's negatively charged, right?
Okay, yeah. But here's the
A
idea. If
balloon?
a balloon, go back to what you said. If this were just the balloon and it's negatively charged, right? This wall is actually neutral, right? Right? So what's gonna happen here? The negative charges here, because this wall is neutral, it's actually made of positive and negative charges all over the place, like that, right? negative, positive, positive, negative, like that, something like that, right? But these negative charges will repel all of these electrons, so they go here, right? So
Mhm.
they all go here. I'll just add another positive here. Now, what happens? This makes the far side negative, right? And also this makes the near
Mhm.
side positive. Okay, now going back to Coulomb's law, right? Let's just write it here. F is equal to K Q1 Q2 over R squared, right? Let's again, this law kind of works in this situation. It actually works only if you have point charges, but it kind of works in this situation because the idea is still the same. What's gonna happen here? Where is this balloon closer to? Is it closer to the positive or the negative side of the wall?
The positive side.
Okay, so balloon is closer to positive side. Balloon is closer to the induced positive side of the wall. So let's just put it here. Then the negative side, right?
Mhm.
So what does this in? So the overall force on the balloon is gonna be attraction. It's gonna be repelled by the negative side of the wall and attracted by the positive side of the wall. But because the positive side is closer, the overall force or the net force on the balloon is attractive. And therefore that balloon is gonna move. Okay? Let's just put this here. Balloon is closer there. So the overall force balloon is attractive. So basically, this balloon is gonna move to the right until it sticks to the wall. Okay. Now,
Mhm.
one more thing here. Let's just draw the electric field now. Now we're gonna consider the wall to be positively charged now, because basically we don't really, sorry, not don't really, but the negative charge and the positive charge. The overall effect is this is positively charged, right?
Mhm.
Okay. In fact, I want to put the negative charges in here for later. I'll just put that there. Okay. So if this were the balloon and this is negatively charged, and I'm gonna put them there, how will the electric field here look like? It's just gonna look like that. That's how the electric field looks like. Okay. This is the electric field between balloon and wall, right? Between the balloon and the wall.
Mhm.
Okay. I'm gonna draw another electric field. There's an electric field in here like this. So this is the electric field inside the wall.
Mhm.
Okay. All right. Is that clear now how we draw electric fields?
Yeah.
All right. Okay.
So
Um.
positive goes outwards.
Mhm.
Yeah.
Mhm. Actually, so what's wrong with what I did? Something's wrong with what I did.
The other arrows
Which
are wrong.
arrows? The blue or the green ones?
The green ones.
No, the blue ones are wrong.
Oh, the blue ones on the balloon.
Which way should they be going?
The opposite direction.
Why?
Because, well, from what you drew, the electrons, no, the
Mm-hmm.
protons,
I remember.
not the proton, the positive charge.
Okay, remember electric fields always go from positive and into negative. So the way I drew them is the other way around, right? They're coming into positive. So these should actually be pointing the other way. So that's what I'm gonna do. Change that.
Whoa.
Okay.
But in real life, you're going towards the wall.
That's the thing. The electric field doesn't really have to do anything with the actual motion of the object. The electric field only tells you the
Oh.
motion of a small positive charge if you place it there in that area. Okay, so it should be like that. Now the motion now depends basically on the other parts of the physics of the situation. Like for example, um, the wall has a much bigger mass compared to the balloon. So which one would actually be moving more? The balloon would, because of the smaller mass.
Mm-hmm.
Okay. Um. So the force is still gonna be like that. Force on balloon. Okay.
Mm-hmm.
Okay. Okay. Is that clear?
Yeah.
All right.
So when it goes onto the wall, it's the protons, no, the positive charge that goes into the balloon's electrons.
If there were
First.
positive charges that could move, yes.
Okay.
Okay.
Wait, does
In
that mean the wall's positive charge or positive charges would go into the balloon, or would it just like stay on the wall since it can't jump out?
Oh, okay, that's a good question. So what would happen later on is because these electrons are on the surface of the balloon. So let's just draw that here. So there's your wall. Here's your balloon. They're touching now, right?
Mm-hmm.
Okay. So these negative charges here, because they're on the surface, they can actually lit jump from the balloon into the wall. Okay. This makes the balloon eventually lose charge, and then later on it will drift away. Okay. So let's put that there. The balloon, upon touching the wall, will transfer some of its electrons to the wall. This makes the balloon eventually lose its charge. Okay, and when it does, it's gonna float away. All right. Okay,
Mm. Oh, okay. Yeah.
makes sense, right?
Mm-hmm.
Mm-hmm. Okay. Anything else you'd like to ask?
Could you positively charge a balloon?
Okay, I won't draw this anymore. I'll just discuss this. Yes, you could, but you have to use
No.
the right material.
Okay.
Okay.
So if it was positively charged, would the protons jump into the wall?
No. What all electrons are always the part or the things that jump. It's always the electrons that jump.
Mm-hmm.
The protons, think about it this way. If the protons could jump, that means they left the nucleus, right?
Oh, right. That makes
And
sense.
if they left the nucleus, what's that basically? That's radioactivity,
Mhm.
right?
Yeah.
Okay. What you had another question earlier, which I want to show you an image of. Okay, if I remember, I'll get back to it. Okay.
Okay.
All right. So, okay.
Is this something about like the arrows? The
What?
question you're thinking about? Like the
Not,
field strength?
not really, not really. Okay. So what we'll do now is
Alright.
again, as long as you get the idea, the equation should be easy to follow and just use, right? Okay.
Mm-hmm.
So, all right. I think we'll go straight to the last bit there. So the last bit was potential difference, right? And defining what it is.
Mm-hmm.
Okay. So this time I'm not gonna compare it to gravity anymore. I'm gonna go straight to the actual electrical bit of it, right? So if you have this big electric charge with charge Q, one, right? And then whether that's positive or negative doesn't matter. So let's just say or negative, right? Now if you have a small positive charge here, so it's again this is our test charge, okay? Um, okay, this test charge has currently potential energy. Um, we don't need to calculate its potential energy. That's on HL. Okay, so let's just label
Mm-hmm.
that at this position, it has a potential energy 1. Okay, and then later on, you did some work onto that charge and you move it here. So now it has potential energy 2, right? And let's say that this small test charge has a charge Q2. Okay, so what's going to be the potential energy here? The potential energy here, or the change in the potential energy, is equal to PE1, PE2 minus PE1, right? Minus PE1.
Mm-hmm.
Okay, now the change in the potential is PE2 divided by Q2, okay, minus potential energy 1 over Q2. Because this term, the potential energy per unit charge, that's your potential. Okay, so the difference in the potential is gonna be that. So this is why it's called potential difference. Okay, and as we said before, potential difference is just measured in volts, because the idea of volts is 1 volt is actually equal to 1 joule per coulomb. Or let's use scientific notation per coulomb like that. Okay. Okay. 1 volt is 1 joule per coulomb, and so this basically means 1 volt is 1 joule of energy lost by a charge of 1 coulomb. Okay. Okay, ready for problems?
Mm-hmm. Yeah.
Okay. Hold on.
Wait.
Go ahead.
Let me read it again.
Okay, I'll put that. You want to go back? Tell me which slide you want to go back while I go look for problems.
No. Okay.
Okay.
Why is volt a joule of energy lost?
Because that's the very definition from here. Because potential is potential energy per unit charge, and potential energy is joules. Energy is joules. Q is charge. So potential
Mm-hmm.
is in volts. We measure potential in volts. So that means um, 1 volt is 1 joule lost, 1 joule of energy lost for every coulomb of charge you have.
Oh, that's why the J over C.
Mm-hmm.
Okay.
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 All right. Let me open up some problems here. Give me a moment. Okay. Have you started your revisions yet?
Nope. We're revising for today. We did a quiz on thermal. I did horribly.
Okay. Thermal physics. Which part? Ideal gas loss or transfer
Uh,
of heat?
transfer of heat is the PV nRT, right?
No, that's gas
PV
loss.
equals nRT.
That's
Oh,
ideal gas.
then I think both.
Okay. Ah. Okay, I'm gonna go get some problems here from the textbook we use. I know we use different textbooks, right? Um, let's keep it easy first. Let's start with this problem here. Okay, here we go. Okay, all right. So go ahead, solve that first. When you're done, I will show you how to solve it. Okay?
Hmm.
Oh, by the way, CJ, I forgot to mention I'm streaming this lesson live, but don't worry, your face cannot be seen. It's just me.
Okay.
Is that fine with you?
Okay. Yeah.
All right then. We can hear your voice though on the stream, but aside from that,
Okay.
okay. No. Okay. So while this is happening, tell me when you're done. I'm just gonna talk a bit.
Okay.
Right. No, just so you know, I can't believe this. Uh, you remember I mentioned my Venus flytraps, right? Mentioned that to you before. Have I? Well, okay. Either way, I made a box for them so they can start. So they can. Well, the technical term is go under dormancy, but I like to think of it as hibernate. So I'm gonna make them hibernate for like 2 months. Okay. Okay. Have an answer yet?
I'm writing the whole equation down and then I'm
Okay.
gonna solve it on the calc. Do you already know the answer? Like,
Except for A, I know the answers to B already. The A
oh,
I still have to like calculate that myself, but it should be easy to go through.
okay. It's just plug in, right?
Mm-hmm.
Okay. So for A, I got 28.48.
28.48. All right, I'm gonna see whether that's. Let's just write that down first. 28.48, right?
Yes.
Is that in newtons?
Uh, but I did Coulomb
Mm-hmm.
over meters.
Okay, if that's the case, that should be in newtons.
Okay.
Okay. All right. All right. I'll solve this now. So we can see how it goes. Okay. So again, Coulomb's law is this: F equals K Q1 Q2 over R squared. We put our K. That's gonna be 8.99 times 10 to the 10 to the 9. Okay. This is gonna be newtons meter squared per Coulomb squared. Okay, that's K. Our Q is 2.0 times 10 to the micro. That's gonna be 6 minus 6 coulombs. Then multiply the other one, 4.0, also in micro coulombs, so 10 to the minus 6. Okay, and finally, divide the whole thing by r squared, so that's gonna be 5.0 times 10 to the minus 2 meters squared. Put those values into your calculator and let's see what the answer is. Um, okay, so I'll just on my trusty calculator do this real quick. This is 8.99 exponent 9 times 2 exponent negative 6 times 4 exponent negative 6 as well. Then divide that by 25 exponent -4. Final answer is 28 point. We have a small difference, but I still got, in this case, the F is 28.8 newtons. So this is my answer. Uh, what do you think?
Is that
Uh,
it?
yeah, this is the answer.
28.8?
28.8.
Why?
All
Why do you
right.
have 48?
Why you got 48? Or maybe I misheard you. Was that 28.8 what you said?
No, I got 28.48.
0.40. Okay. All right.
48. I got 0.48.
Okay. All right. Oops, sorry. Wrong one. Okay.
No, I see my mistake. Okay.
Okay. So it's a mistake on your end, right? So that means,
Yeah.
okay. Good news though here is that's pretty close. So I think you got it right for the
I
most part.
missed the 8.99. I only put 8.9.
Ah, okay. Well, in that case, if you use only 8.9, your answer should be acceptable.
Oh,
All right. So yeah,
okay.
in other words, yeah, you're okay. Let's just note that. Okay. I'll just
Yeah.
note that here that K here is 8.9, right? Okay.
Hmm.
It's better to round that off as 9 though. So that's going to give you a slightly more accurate answer.
I didn't mean to round it. I think I just
Mhm.
forgot to put it down.
The 9 9. All right, in that case, it's fine then either way, yeah? So let's go to B.
Okay, so BI is the force between the charges is a quarter of what it originally was.
All right, I'm going to write it like that.
Yes, and
Okay.
then number two is F divided by 2.
F over 2,
Is
correct.
it?
It is. Great. And the last one?
And then F, just F.
F, no change.
F is F. Yeah.
Yeah, all correct. Okay, great. Coulomb's law done. I think you got how to do that. Let's move on to the next
I wish
problem.
the IB exam questions were like this because like it's like very direct, very clear.
Mm-hmm. Now, at this point, I'm still giving you the easy problems. Okay.
Uh,
Um.
yeah.
Okay. Calculate the force. Okay. I'll give you a difficult one. Rather difficult one.
No. I mean, I wish my exams were like these questions. I'm not saying I can't do or I can do these easy
Mm-hmm.
questions.
Well, later on, we can hope for the best. All right. Here. Calculate the force on the charge Q when uh
Okay.
we're gonna do Q is equal to 3.0 microcoulombs.
Okay.
Okay, do you need a hint here?
Do I use the Coulomb's law
Uh-huh.
twice?
Correct, you do.
Okay, so I'll start with the. Can I start with the 4 centimeters one?
Mm-hmm. Yep.
Okay. Um. Okay. So can I do like 8.99 times 10 to the power 9 multiplied by negative q multiplied by 2q or no?
No, because you can do that. You can do that if we were looking for the force on negative Q or 2Q. But that's not what we're looking for. We're looking for the force on Q. We're looking here. Okay. So what's the
Does
force?
that mean I do 3 centimeters instead?
You have That's one of the distances you have to consider. Yes. The 4 is going to be useful later.
Later. Okay.
Mm-hmm. Can I give you
Um.
one clue?
Yes.
Okay. Excuse me. 3, 4, and they're at right angles. So that kind of forms a right triangle. What's the hypotenuse for a 3, 4 triangle? What's the length?
Hypotenuse for a 3-4 triangle.
Uh-huh. So basically, what I mean here is if you have this kind of
Oh,
right.
a squared plus b squared.
Mm-hmm. This is a useful
Yeah.
shortcut for you to learn. Okay, so I think I'll teach you the shortcut. Yeah, you can do the Pythagorean
Okay.
theorem there, but the useful shortcut is if this is 3 and this is 4, you could reverse these two. Okay, this is 5.
Mm-hmm.
That's automatic. You can
That's always like that.
yeah, it's always like this. As long as either leg is a 3 or a 4 unit length, then the hypotenuse will always be 5. You can check that with the Pythagorean theorems.
Okay. So we know the length, but
Mm-hmm.
what does that length help us find the
So let's label that there.
force?
This will be 5, right?
Yes.
That's gonna be helpful for something.
Okay.
Okay, what's the?
Wow.
I'll give you another clue here. Okay, what's the force from 2q? From 2q, and what's the force from negative q? As you said, you use
Um.
Coulomb's law, right?
Yeah.
Mm-hmm.
I think it the from negative q to q is just a negative q.
Mm-hmm. So which way is the force directed? Up or down?
Um. Down because it's going towards the negative, right?
Mm-hmm. Or remember, another way you can think about this: if the force is negative, it's attractive. If the
Mm-hmm.
force is positive, it's repulsive.
So if the top q was a negative q and the bottom was positive, the arrow would be pointing upwards,
No, still pointing downwards.
even if the top q is negative q.
Yes.
Okay. Why?
Because they're gonna attract each other, right? If you really want to keep it simple, the best way to keep it simple is just look at the charges. If they're negative and positive, they should attract each other, and you give the directions accordingly. That the two charges should attract each other. If they're both positive or they're both negative, they should repel each other. And again, you should make sure that those force arrows are in the appropriate direction so they repel each other. Okay. So what do I mean by that?
Wait, so if the bottom was positive q and the top was negative q, it would still be going down?
Yeah, positive Q
Okay, okay.
and then negative Q here. What do you get?
You
This positive Q
an
will go
attraction.
down, and then this positive Q will go down. This negative Q will go up, right?
Hmm.
So similarly,
But the
if
positive will go down
yeah,
because the positive goes to the negative.
yeah. So if this is
Okay.
negative Q and positive Q on this side, then yeah, you're still gonna have to draw that. If you're looking at positive Q, then F is upwards. In this case, F down, right?
Okay. Why are the line lengths
They should be the
different?
same. They
Is
should be
there a
the
reason?
same. They
Oh,
should be the
okay.
same. All right. Guess I'll erase this. Oh, by the way, your question earlier for calculus, I think you've read it already, right? You've read my answer
Yeah.
to it. Is that okay with you?
Yeah, because I mean, college, like, I've only taken differential calculus
Mm-hmm.
in Math AI.
Mm-hmm.
So, like, honestly, I'm not even ready for, like, computer science.
Oh, okay. So yeah, that should definitely help you later on. So okay, sure.
Yeah. I don't know how I got in for computer science. Yeah. I despise physics and yeah,
yet,
I don't know.
yet you're here. Well, you wouldn't be here if you
Oh,
like
it's
physics.
interesting. I don't like the math part. Yeah.
Yeah, a lot of students
I
would
like,
say that
yeah,
they like the physics part, but they don't like the math part.
exactly. Like, watching it and listening to it is interesting, but when you have to do it, no. I don't know.
uh, it's a good thing I like math too.
Yeah. I love Math AI because it's all about like concepts.
Mm-hmm.
in common sense.
Not too
Yeah.
many equations, I guess.
Uh, nah, not really.
Well, compared to AA. All right, you have an answer yet? At least for one of the charges.
Oh, um, well, wouldn't the charge from 2q to q be like 2q squared?
Yes, correct. It is.
And then the negative q is just negative q.
No, not negative q. It's gonna be. You said 2q squared earlier, right? Because you're multiplying q and negative. Sorry, you're multiplying q and 2q, right?
Yes,
So you're gonna have to do the same thing. The same thing. You're multiplying q and negative q. So what's that gonna give you?
negative q.
Squared.
Oh, yeah.
All right.
Sorry.
Okay. I think you got an answer for one of those already. Have you?
One of which.
Uh, one of the one of the forces.
Negative q is negative q squared, you said.
Mm-hmm.
Wait, is that not the force? Oh, that's
Yeah,
not the
but
force.
remember, you're given the actual value for q.
Oh, okay.
Okay, the annoying bit, the data
It's
that you
36
missed. Okay, 36.
from
Mm,
2q to q.
okay, from 2q to q. Okay, I'm gonna do that real quick. So f from 2q will be equal to. I'm gonna use 9 this time to make it even easier. 10 to the 9, right?
Mm-hmm.
Times um 2 times 3 times 10 to
Yeah,
the
man, I
minus
think I did wrong.
6 times the other one would be 6 times 10 to the minus 6, right? Over
You have to do this.
5 squared.
Oops. Wait. Um,
Mm-hmm.
where's
Okay, I'm gonna
why is
remove this. Sorry. Should be like that.
yeah.
Okay. And then for f on q1, f from 1, from negative q rather, would still be the same, but I'm still also gonna use 9. I just want to make that point 0 times 10 to the 9 times 3 times 10 to the minus 6. Hold on. I'm gonna move this so
Is it
it's
5 times 10 to the negative 2?
hold on. Oh yeah, you're right because it's in centimeters. So that's gonna be 5 times 10 to the minus 2 squared, right?
Mm-hmm.
Okay, great. So you spotted that. Great. Then this other one here, back to negative q, you're gonna put the negative 3 here times 10 to the minus 6. All over, same thing, 5 times 10 to the minus 2 squared.
And do we add those two forces?
Yes, but how do you add them? Because remember, forces are vectors. You don't just add the actual numbers together.
Yeah.
Okay. Mm, you have to figure out what this
How do you
angle
do that?
is. We have to figure out what this angle is.
Oh, wait. I think I got this.
Mm-hmm.
I can use this. Can I use the sine rule?
Yes, you can.
Uh, Math AI coming in.
Yes. Actually, okay, even though in physics, just so we're clear, yeah, even though in physics you're expected to do it like the old-fashioned way where you really have to look for theta by using sine or cosine or tangent. If you know shortcuts like the sine rule or the cosine rule, you can use those perfectly, no problem.
Like, are those actually okay? Like, do they always work?
They always work. They will always work.
Okay. And I got 39 or 30, 30 no, 37 or 36.9.
Okay. I just know this from memory. This is approximately 37 degrees. So we'll use 37
Yes.
degrees from memory, correct? So, uh, whatever this is, whatever F2Q and FQ are, how the final part of this would be F is equal to um how
Cosine rule? No,
little bit
not
of sine
cosine
rule,
rule.
but this is what I'll do. This is gonna be F from negative Q. So Fy, I'm gonna write that Fy is equal to F negative Q plus the force from 2Q along the y-axis, right? And then Fx is equal to F2Q along the x-axis only. So this will be whatever this value is. I'll just write this still as F negative Q. Then, as you said, this is gonna be plus, this is upwards. Sorry, this is downwards, right? That's a negative answer. Okay.
Mhm.
And then the other one would be you add um, F2Q, then sine theta, or that's 37 degrees, right? Let's put that. Then similarly here, this will be equal to F2Q cosine 37 degrees. So once we find these values, just calculate, and then finally, final answer here will be F is equal to square root of Fy squared plus Fx squared. Why is it like this? Because again, this is forces acting in different directions, but on the same object. So you have to kind of do it by component to make it easier.
That's Pythagoras, right?
Yeah, it is. It is.
Okay. Wait. So okay, so I got for the 2Q force thingy
Mm-hmm.
64.728. Do I
Okay.
square that
What you got? Sorry.
or square root 64.728?
64.728. Okay, and then you square that here, right?
Yeah.
Okay.
And then the other one's a negative though.
Yeah, it should be a
I thought you
negative.
squared.
This
Okay.
this is gonna be the negative, but if you square it, it doesn't really matter, right? Now, what does this mean?
Mm-hmm.
These two together, the overall result is still downwards.
Right.
Okay, and then okay,
I got
and
56.1.
okay, okay, 56.1. All right, so let's go all the way through it now. So let's put the numbers in. Let's just see if you got the numbers right. Okay, so okay, all I gotta do is do the other one. So 9 exponent 9 times 3 exponent 6 negative 6 times 3 exponent negative 6 again, then divide that by 25 exponent negative 4. Okay, so this is gonna be 32.4 for negative q. So I'm just gonna put the magnitude in here. So I'll just put the negative sign, but 32.4 newtons. And then this one is gonna be 64.8 newtons. Okay, so let's continue here. What do we get? Um, 30. Let's do that one. Okay, so let's do the other one. 37. Take the sine of that. Times what's that? 64.8. 64.8. 64.8. Okay. Then that's repulsion, so that's gonna go up. Then we subtract the other one, which is how much is that again? 32.4. 32.4.
Yeah, I don't really understand the cosine. Is that like cosine's like the is that on the x-axis or the y? No, that's on the
Okay,
y.
In this case, the cosine is on the x-axis.
Okay.
Okay.
Does it tell us the direction of the arrow?
No, it doesn't. It just tells us this angle. Just tells us that angle.
Okay.
Okay. So let me just get the values in. This actually got me a positive number. This is gonna be 6.60 newtons. Okay. And then if we do the other one, 64.8 times cosine of 60 64.8 times cosine of, what was that again? 37. Cosine is gonna be 51.8 newtons. Okay, so what are we gonna do? So I think you got this, and I think you got this. So finally, we just do the square root thing. Now 51.8 squared plus 6.60 squared. So if we square this times 6.60 squared, oh sorry, not times, plus. Okay, let me try that again. 51.8 squared plus 6.6 squared, and then we take the square root of that. This gives us 52.2 newtons F. Let's go to that. Okay, and finally, it still asked us, if we go back to the problem, it's asking us, never mind, it wasn't asking us for direction. Oh, it is magnitude and direction, right? So the direction
Mm-hmm.
would be, we use sine or cosine rule again, or maybe Pythagorean theorem again, with these values to find the angle. Okay.
Wait. How'd you get the Newton's thing? Like, I need like a step by step
All right.
because
So
like,
okay. So
yeah, I
let.
couldn't see it.
All right. So I'm gonna start from the beginning again. Yeah. So just to make it
Okay.
easier. All right. Let's delete everything here. So everything, at least the setups here, right?
Mhm.
All right. So step by step, let's start with, I'm gonna color code this now. Okay. So the first force is that, and we'll label that F negative Q, right? So F negative Q is all on the y direction, right? And that's gonna be 9.0 times 10 to the 9 times Q, 3 times 10 to the minus 6 times negative Q, negative 3 times 10 to the minus 6 all over our r squared here should be, I think I made a mistake earlier. This should be 3.0 times 10 to the minus 2 meters squared, right? Let's remove the meters here. So what are we gonna, so if we calculate that, it's gonna be 9 exponent 9 times 3 exponent negative 6, 9 exponent 9 times 3 exponent negative 6, then times itself, so basically that's squaring it, then divided that by 3 exponent, no, let's put it straight away, 9 exponent negative 4.
Wait, what?
Okay, I just put in that in the calculator. This is uh basically, if you calculate this, put this in the calculator, this is gonna be 90 newtons.
9 exponent 4?
Okay, this becomes 9.0 times 10 to the minus 4 because of the square part here, right?
Right.
Okay, so once you put that in the calculator, F negative Q is 90 newtons. And let's just put the direction in. This is down, right?
I got negative 90 though.
Which is fine.
Okay.
Okay. All right. Since we do have a negative sign in there. Let's just put that negative in there. It's fine either way, right? Now
Mm-hmm.
we do the second one. This bit. Oh, sorry, not that bit. This bit, right? So f from 2q will now be equal to the same thing, 9.0 times 10 to the 9 times 3.0 times 10 to the minus 6. Then this time the charge is 2q, so that's going to be 6.0 times 10 to the minus 6. The distance now is 5. So
Yes.
5.0 times 10 to the minus 2 squared. Putting that in the calculator again, just like earlier, this is gonna be equal to 25 times 10 to the minus 4. That's the value I'll be putting
Right.
in the calculator. Okay. So again, so I'll
Okay.
say that here, calculator. What am I gonna put here? 9 exponent 9 times 3 exponent negative 6 times 6 exponent negative 6. Then divide that by 25 exponent negative 4. That's going to give me 64.8 newtons. So F,
64.8.
yeah,
Okay.
2Q.
0.7.
Oh, because I think you used 8.99, not 9.0.
Okay.
Because I used 9.0, right?
Mm-hmm.
Okay. So again, in the exam, which one do you use? The most accurate version, 8.99, right?
Mm-hmm.
All right. So in this case, either way, if you use 9.0, we get these answers. So if we continue, what do we do now? So if we go back,
Um,
I'll erase this bit.
Pythagoras
Yeah,
to find the force for the top point.
yeah, correct. Okay, so,
Okay, now it makes sense.
okay, it's making sense now. All right. Now, I'm going to show you a trick. This works for any problem wherein you have to resolve forces. Okay.
Oh,
All right. The trick I always teach my kids is this. You always make your table, and then let's put XY here. Okay. How many forces do we have in this problem? We have two. We have the force from Q, negative Q, right? And then we have the force from 2Q, right? I think I've shown you this trick before.
mhm.
But the easiest way to do this now is, sorry, let's not say that's F. Let's say that's the sum of the forces. Okay. Now, um, in this case, this is gonna be Fx, and this is gonna be Fy, right? Now, in this case, this is 0, and we know this is downwards, so we can keep the negative sign, negative 90, right? Now here in
Mhm.
2q, we have to kind of take into account the direction. So if we look here, or rather, if we look here, this q is going to move that way. So it's going to move up and left, right? So if it's going to move up and left, this means this is positive and this is negative. Or the other way. This is positive and this is negative. Okay? So what are we gonna put here now? This is gonna be, as we said before, if you use trigonometry, this is 37 degrees.
Yes.
Okay, so from 37 degrees, all we're gonna do now is put our value in. For F2Q, that's 64.8 newtons. This is 64.8 um, cosine of 37 degrees, right? And this is
Mm.
gonna be 64.8 sine of 37 degrees. Okay, why the table? This helps set up our equation. The first equation we get is that fx is equal to negative 64.8 cosine 37 degrees. Just calculate that and that's fx, right? So what's that gonna give you? Um, let's calculate that. The 64.8 times cosine of 37 is 51.8 degrees. Okay. Sorry, not 51.8
Mm-hmm.
degrees, 51.8 newtons. Okay. Now Fy will be equal to um negative 90 plus 64.8 sine 37 degrees. Put that in the calculator again. 64.8, oops, 64.8 times 37 cos, take the sine, then minus 90. This gives us negative 51.0 newtons. Okay, finally,
Mm-hmm.
we need to do two things. Okay, so what's gonna be, it's gonna be f, it's gonna be fx squared plus fy squared. Take the square root. Okay, so if you put that in the calculator, that's gonna be 51.8 squared. So let's square that already. 51.8 squared plus 51.0 squared. 51.8 squared. Okay, and this is gonna give us once we do the math part, this is gonna give us 72.7 newtons. So that's the first part. How about the angle?
Wait. I'm
Okay,
sorry.
where'd you get lost?
Oh, I forgot the negative 90. Where I was wondering, like, why is it negative 90?
It's to the left. Ah, sorry, it's downwards. Going back to the problem. So again, let's remove all of these again. Because Q is attracted to negative Q, Q is gonna go down. Hence, going down,
Mm-hmm.
negative. Okay. Now Q is repelled by 2Q, so it's gonna go that
Oh,
way.
sorry, it's negative 89.9. Yeah, sorry,
Yeah.
I forgot we did the math earlier.
All right. So our answer is gonna be slightly different because I used 9.0, right?
Mm-hmm.
Okay.
Wait, I need to like think of the equation in my head again.
Okay. Sure.
Um, you for the top one you got 0, right?
Uh,
Why? For F like
here.
X. Yes. F
Okay, because
minus
Q,
G.
if we go back here, negative Q, all the force is vertical. All the force is upward, downwards, right? It does not exert a horizontal force on Q.
Mm-hmm.
2Q exerts that force this way, right?
Mm-hmm.
That means it's exerting a force going this way, and the component of that force, and a component of that same force is going upwards, like that. So again, that's our actual arrow. This is the horizontal component. That's the vertical component.
Yeah.
Okay, so
Well,
that's
why is it
why
a 0 then?
this one.
Yeah.
Okay, because we're looking at Q. Q, the force from Q is all downwards. There's no horizontal component to it.
Yeah.
That
Oh, the X doesn't go for. Oh, okay.
Yeah. Okay. So no horizontal component, no x component for the force. That's why that's 0.
Mm-hmm.
All right. So we got this. Our final answer is gonna be
Wait,
what?
wait.
Okay.
It's negative 90 plus 64.8 sine 37 because of it goes down. Wait, no. Why is it?
It's just this. Whenever you have this table, all you have to do is copy everything. Negative 90
Mm-hmm.
becomes negative 90. The 64.8 sine 37 is there. And then the Fy is this.
Hmm. Oh, okay. The table makes sense.
Mm-hmm.
Because wait, let me like explain it out in my
Okay.
head or
All right.
like to you.
All right. Go
So
ahead.
you use the F equals K Q1 Q2 over R squared
Mm-hmm.
for the but you do that for the Q to the negative Q and you
Mm-hmm.
say that's the X will be 0,
Mm-hmm.
but the Y will be 90. negative 90 because it's
Right.
going down.
Yes.
And that's the answer I got with if I use that equation for those.
Correct.
And since the force is negative 90, you use that plus 64.8 because it's a positive, or that's the direction.
Right.
It's going towards. It's going towards F2Q or the 2Q, right?
Not towards, away from, because again, 2Q is gonna
because the
repel it.
positive goes to the negative.
Yeah, so it's gonna be repelled like that. So away from. But the magnitude of the force is still the same. Okay.
Okay, I think I got it.
All right. So finally, let's just finish this bit now. So we got our force, the magnitude of the force. How do you find it? How do you find this angle? We're gonna use that again. So tangent theta would be equal to, let's go back. If this is our theta, that's gonna be, tangent is opposite over hypotenuse. So y over x in this case. So it's gonna be 51.0 over 51.8. And that's gonna give us an angle equals tangent inverse of 51.0 over 51.8. Okay, and therefore finally theta is, if we put that in the calculator again, 51 divided by 51.8, then inverse tangent, that's gonna give us 44.5 degrees or 44.6
Wait,
degrees.
why are we finding that angle? Oh, we're finding angle the positive Q.
Yeah.
For what?
That's part of the instructions. You're supposed to find both the magnitude and the direction. So the angle gives you the direction. 44.6 degrees. Okay. So again, going back to the instructions, magnitude and direction. Okay. So in other words, that's almost. So in other words, it's almost 45 degrees. So it's going to basically go. This thing is gonna go that way. Oops. It's gonna go somewhat like that, and an angle of 45 degrees. That's the force.
I see.
All right. Is that clear? Let's zoom in to.
Yes.
Okay. Let's just zoom in a bit to see that. Okay. All right. Let's. Okay. Like I said, that was a bit challenging. Let's go to another easy one before we take a quick break. Yeah. Or you want to take a quick break first?
I want to do the question now.
All right. Okay.
Like a similar one.
Similar one. Okay. This one's a bit easier because they're all in a line. Okay. Okay. So these three charges are in a line, so it's a bit easier. You don't have to do the table, but you still have to take into account charges, whether they're positive or negative. Okay, we're looking for the net force on the middle charge. Okay. All right. So while you do that, I'm gonna go just take a quick sip of water, and I'll be back in like a minute or two. Okay.
Okay.
All right. I'll just go on mute, but I won't change the screen. All right, I'll be right back. I'll just go take a sip of water. I won't mute it here though on the stream, so I'll be back soon. right, I'm back on the stream and let me get back to CJ. All right, I'm back, CJ.
Okay, hi. Also, I was wondering, like,
Mm-hmm.
what's the thing where you combine the Coulomb's law and the electric field strength equation?
Oh, that's let me just do that real quick on the just on this bit here, yeah. So Coulomb's
Mm-hmm.
law, so let's just write that here. F equals K Q1 Q2. Well, let's use the other form. That's big. Let's use the big and small q's, yeah. So Coulomb's law, so K big Q small q over r squared, right? And then the electric field strength by definition is equal to the force per unit charge. This is definition, right?
Mm-hmm.
Okay. Now remember that Coulomb's law works for 2-point charges, right? Okay. This doesn't really
Yes.
work for other configurations, but it can help us with other things, right? But so what does this mean? If you combine these, what's the electric field of a point charge?
Is that um, like how where on the line does the point have to be for one of the spheres to
As
feel
okay,
charge? I don't
all
know.
right, I get what you're trying to say, right? So let me just say it again. So you're asking, tell me if I'm wrong, okay? Basically, you're asking, how do you know where that charge is, where a charge is compared to another charge? Where do you know on which
Yes.
field line it is, right? The answer to that is it doesn't really matter. The field lines that we draw,
Oh,
the field lines that we draw are just representations. The field itself is always there, whether you land on the line or not. Okay. So again, the line itself doesn't really matter. What matters is it's where the charge is basically here. So let me just redo that to be sure. So this is your big charge Q, right? And then let's say this is your small charge Q, right? So basically you're asking, how do I know that this charge is on that line, right? Is that it?
mm-hmm.
Okay. You don't have to do that. All you have to know is that these two are separated by some distance r. Okay, because if I draw the field lines like you would normally draw them for big Q, you would normally draw it like this, and it doesn't really hit the field lines, right? But if
Mm-hmm.
you want to be more strict, you can actually draw more lines so that you can hit that charge there. Okay, so that's why I said it doesn't really matter if you hit it or not. What matters is you have two charges and they're separated by some distance. Okay, so what's going back to what I was saying? Um, so the electric field on a point charge is I'm gonna use this. It's gonna be F of a point charge over Q, right? But let's just write it in 4-point charge, right? 4-point charge. So what's our equation for the force on a point charge? It's that. It's Coulomb's law. So all I'm gonna do now is replace everything. So E equals RF is now gonna be K big Q small q over R squared. Divide that by small q. That cancels out. We're left with K big Q over R squared. And that's how we got the electric field equation for a point charge.
Mm.
E for
Yeah, and then if you want to do the other point, you just use the other Q.
use the other Q, exactly.
Okay. Okay, that makes sense.
Okay.
I got the answer, I think.
All right. So what's your answer there?
So, wait, I use the Q1, Q2, right?
Yeah.
The
Okay.
Coulomb's law.
Just so we're
Okay.
clear, it's exactly the same form. It's just different in terms of the notation, but it's the exact same law.
Wait, I used that for this question?
You can again doesn't matter whether you use Q1, Q2, or you use big Q, small q, they're equivalent. What
Oh,
matters is you plug it in properly into the equation.
wait, I used two equations.
Okay, but you will
No, I
use,
mean two. I made two equations
yeah,
for
you
using
have
the
to.
same equation.
That's correct. You have to do that. All right. So what's your overall answer?
Uh, wait, I added F1 and F2.
Mm-hmm. You added them.
Is that okay?
No, you have to subtract them.
Okay.
Why?
Well, they were both negative.
Why? Yeah, even though they're both negative, remember you have to take into account the actual direction of the motion,
Oh,
right?
I got 89.9.
89.9. That's right.
Like positive.
Positive. Newtons, right? Okay. Now
Yes.
I'm gonna do this again on the regular manner first. Okay. So let's say that this is F1 going that way, right? And then F2 is gonna go that way. You know what? I'll be more consistent. I'll use F4 for 4 columns and F3 for 3 columns. Okay. So okay, what's F4 equal to? F4 will be equal to again K times 4 I'm gonna just keep it like this first. 4 microcolumns times 2 microcolumns microcolumns over 4 cm squared, right? And then what's F3? That's gonna be K times minus 2 microcolumns times 3 microcolumns all over 2 cm squared. Of course, afterwards you convert everything to the proper units like columns and meters. But basically, what do you do here? So once you can, never mind. So let's convert that now. Let's change this 10 to the minus 6. This is also 10 to the minus 6. Minus 10 to the minus 6. The 4 becomes 4.0 times 10 to the minus 2. 4 times 10 to the minus 2. Similarly here, minus 6, minus 6, minus 2, and our k is 9 times 10 to the 9. Again, I'm just using 9 to the 9 to make it easier, right? If you use 8.99, that's also fine. Times 10 to the 9. This is times 10 to the minus 6. 10 to the minus 6. This is 10 squared. So what will we get? This is what I'll do. I'm going to cancel that. Never mind. I won't cancel anything. So let's just calculate that again. All right. 9 exponent 9 times 4 exponent negative 6 times negative 2 exponent negative 6, then divide that by 16 exponent negative 4. Okay, so this is going to give us 45. So the first one, 45 newtons. Okay, the second one, F3, we do the exact same thing. 9 exponent 9 times negative 2 exponent, oops, I forgot the negative. We'll put the negative in a while. Okay, so all right, so 9 exponent 9 times negative 2 exponent negative 6 times 3 exponent negative 6, then divide that by 4 exponent negative 4 squared. And okay, I accidentally clicked on few buttons. Too many buttons. uh, by 4 exponent 4 negative. Okay. Okay, this is going to give us 135 newtons. Okay, so
Yes.
all right. So in this case, how do we assign the signs, whether positive or negative? We look at the problem and see which one is to the right, which one is to the left. F3 is to the right, so we'll assign this positive, right? And then F4 is to the left, so we'll assign that a negative sign. Even though we both have negatives here, okay, we still have to.
Wait.
Okay, because if you just calculate that, you get negatives either way.
Yeah. Wait, so how do you know it's going to the left and that's going to the right?
Okay. Good question. All right. Let's take a look. This is a negative charge. This is a positive charge. They should attract each other. So if they attract, to the right.
But I thought the positive charge goes to the negative charge.
It does, but again, we're not interested in what the positive charges do. Our question is about the negative charge. Net force on the middle charge. Get it?
No.
No. All right. So let's make that bigger first. Okay. So again, that's our line. These are our charges. I'm not putting the numbers. I'm just saying that's positive, negative, positive, right?
Yes.
Okay. So the question was, what's the force on the middle charge? So basically, what we want to see here is how this negative charge moves. Okay. So again, the question is basically saying asking which way will this charge go? Knowing that it's stationary, so that means that okay, so due to the force. Okay, so if we know, let's just put the numbers back in. Okay, so we know that this force, this charge, okay, I'm gonna color code it again. I'm gonna turn this red. This is red, right? And then this is green. So we're gonna color code that so that we can color code the arrows as well. So this force, this negative charge is gonna be attracted that way, right? And this red charge is gonna be attracted that way, as you said. But look at the question. Are we interested in this thing? We're not. We're not interested there. Even though we know it's gonna move left, we don't care about whether it moves left. We care about only that. So the only force we want to look at is not that dot, it's not this force anymore, but just that other force. Okay? So again.
So it just points outwards because it's attracted to that.
Yes. So,
but earlier you said like the positive goes to the negative charge.
Yeah, that does. It is. Because this positive thing will move this way. Right? But the question again, CJ, is not about this charge. It's not about this charge. The question is about this charge. So even though this will happen, we don't care about that in the problem. Get it?
So because the answer is positive, it will go right. But then you drew an arrow pointing left as well.
Oh no. What I mean here on this arrow pointing left is again. Okay, I'm gonna.
On the other side. Sorry. On the green one.
Oh, on the green one. So we do the green one. So if we do the green one, it's the same thing. This will move that way. That will be attracted that way. And this green thing will be attracted that way. But again, we don't really care about this one. So we ignore that arrow, just like we will ignore this arrow. So if we ignore all these other arrows and just focus on the arrows on this middle charge, it's basically that. This is the way our arrows look like. Now, of course, we want to be accurate. We want to be accurate and say that one arrow should be bigger than the other, right? And that's what we calculated here. This F4 is our green arrow. This 135 here is our red arrow. So if we put that here, this is a 135, and then we're gonna make this a bit more accurate by making this shorter, right? So this is gonna be 45.
So it doesn't matter if it's positive or negative.
It doesn't matter at this point anymore, because again, there is a way to make it have the correct sign mathematically, but the math is a bit more complicated than what you would like. So it's a lot easier to just think. So the tip here, so I'll just put it here, okay?
Yeah.
Okay, the tip here, it's easier to work with the magnitude of the force instead without the sign, okay? Magnitude of the forces, no sign, right? Then assign plus or minus on the actual diagram. Okay.
So are these forces starting from the electron and going towards their respective points, depending where the equation was from?
So this would be,
but
that's
from
correct.
The negative charge.
So in this case, what's the resultant force? That's gonna be 135 minus 45 newtons, right?
Which is 90.
Which is gonna give you 90.
So that's the resultant. What's resultant force?
Yeah, that's the resultant force on the middle charge. Okay. Okay, you tell me before we continue. What's the confusing part? There's still something that confuses
resultant
you.
Force.
Resultant force. Resultant force. Basically, you're just adding your forces with directions. Okay. This is
so
actually.
What direction is what direction is it?
So in this case, we got a positive. So this is to the right. Okay. Okay. All right. Why did we assign negative here? Because this is left, right? So there's a negative here. This is a positive because this is to the right. Okay. So
if 135 was on the left, it would be like negative 90.
Yes, correct. If they switched places, then the answer would be negative 90. You would interpret that to be like to the left. All right. Getting it now? Getting it?
Yeah.
All right. I think the reason you're missing this is from topic 2. This particular part of the problem solving process is from topic 2.
Yeah, it looks like mechanics right now. It looks like friction.
But here's the thing, yeah. Especially which topics? Topic 5, topic 6 will still involve mechanics. Specifically forces. Okay. So you really need to get back to forces later on. All right. Okay. Next thing. All right. We have like around 20 more minutes.
Wait, for Sunday, could I review mechanics?
Sure.
Like, could we go back to mechanics?
Sure.
Like, can I also move like an hour from Thursday to Sunday?
Let's see if I can do that right now. So this Sunday we have 1 hour. So you want to move one of Thursday's sessions to this Sunday or to next Sunday?
This Sunday, like
this Sunday.
The following Thursday's hour to this Sunday from 5 to 7 p.m.
All right, I'll move that then. Hold on, I'll change that right now. All right, so while I change that, that should be the 21st. I'll just change it to a bad time first, then I'll fix it. As requested. Okay. All right, so this Sunday, I'll just fix the calendar now. There. Okay. Okay. Um. Okay, I'll just fix it later, but I've already put it to Sunday. But I put it at 8 for now. Okay. I'll just fix it later because there's something on my calendar blocking it, but I can move it later on. Okay.
Mm-hmm.
All right. So anyway, let's do one more problem. This time I'm gonna pick an exam style problem. Just about Coulomb's law, basically. Hmm. Where is that? Okay, here. I'll just give you like a couple of multiple choice problems for now. Okay, that still involve both the electric field. Okay, and okay, just electric field for now. Okay, multiple choice. What's your answer?
Okay, let's see.
Just give it a bit of space so we can write. Mm-hmm.
What should I draw out the first question or no?
You don't have to. It's gonna be
Okay.
helpful to do it though. Yeah, drawing's always helpful, even if you don't have to. It from my experience, this is even me right at this moment, yeah. There are cases wherein even though I know I can solve it without the equations, without the drawings, it makes me solve it much faster if I draw it.
Mm-hmm.
Does it kind of like um you see what's happening. It's a lot easier to see what's happening in that case.
Can I say that like okay, they both experience the same force, right?
Aha, correct.
Or so that would mean F is isolated.
Uh-huh.
So is it C? No.
Created by. No, it's not C.
Oh,
I'm gonna give you a hint. Hint. Definition of electric field.
oh, E equals Q or KQ over R
Nope,
squared.
that's not the definition. That's the formula
Oh,
for a point charge.
I don't know the definition.
Definition is okay. I'll say it now to help you out. That's the definition.
Yes.
Okay, so that should eliminate
Uh,
two answers, right?
A and B.
A and B are the correct are possible answers. So C and D are wrong, right?
Mm-hmm.
Okay, now which Q is it that you have to use? Big Q or small q?
Okay. Which one did I get rid of?
All right. Uh-huh.
So like at the from the position of Q. So Q is like the main focus.
Correct.
So it's probably B. No.
Correct. All right.
But
Okay.
if it was from the position of big Q, would that be A?
Yes. Yes, that's also correct.
Okay.
So the one creating the field is not the one experiencing the force. Uh, that's one way. That's one way for me to kind of remember it. The one creating the field does not experience its own force, right? Not
Mm-hmm.
experience its own force, and thus, okay, thus cannot experience or cannot feel, right? Cannot
Mm-hmm.
experience its own electric field. Okay, so this is the way I like to think about it, but I hope this is useful for you to get to it.
Mm-hmm.
Okay, so in this case, using this idea means it cannot be big Q because the one creating the field is Q, big Q. All right. Okay, so let's do this last one for today. Let's do number two. Um,
Mm-hmm.
in which regions can the electric field strength due to the two particles be zero? I'll give you a clue
Mm-hmm.
here just to make it easier. Think vectors. Think vectors. Okay. If you don't know this yet, it's fine. You can kind of figure it out either way.
Q's going left, right? And
Uh,
two Q's going right.
if we're talking forces, yes. So you
Oh,
have,
that's not vectors?
yeah, forces are also vectors. But remember, in this
Yeah.
case, vectors, we have forces, we can have electric field strengths, right?
Mm-hmm.
So the idea here is when you think electric field strength, you just think which way are the arrows pointing or pointing for that particular charge. Is it away or towards the charge? So here, think motion. In electric field, think um pointing.
Hmm.
Okay, so because we have electric field here, we need to think which way is it gonna point. Okay,
Yeah.
so for 2q, which way is the electric field gonna point?
Can I say right?
Always to the right. So it's like this.
Yeah.
No,
Wait. Oh,
not quite.
from the left one goes left.
Ah, there we go. And then we don't really need everything else because we just need the thing on the line. So we'll just do that, right?
Uh,
How about for negative q? Which way is the electric
Um,
field?
left.
Hold on, I'll make this a bit bigger so we can see this better as well. So this one is to the left. Is it
Oh, to
like
the
that?
right. Oh, okay. Yes.
No,
Is it not?
one is
Oh,
wrong.
the
Again,
one on the right goes right.
no, it's negative. So negatives always point inwards like that.
Okay.
Okay, so think about it now. So what I'm gonna do is I'm gonna draw this even further all the way up to here like that, and I'm gonna draw green another line all the way up to here. Okay, now where do you see the electric field strengths or the electric field directions like going against each other? Sorry, I think this is wrong. This
At
should be
two.
okay. It's not at 2. Look at 2. They both move to the right. At 2, they both point to the right. Both
Mm-hmm.
point to right.
Then but at three they both go opposite or like other ways.
Okay, so in 3, opposite, right?
Mm-hmm.
How about in 1?
I can't see one. Like it's cropped out.
Ah, okay. I'm going to how to move this. I'll fit it first and then I'll zoom
Oh, I see
like
it.
this.
Yeah, at one they're like going opposite directions as well. Do
Opposite
they
as well,
cancel
right?
each other out?
So they can it is possible to cancel each other out. It's not asking if whether they will, it's just asking for a possibility, right? So all of this is also basically opposite, right?
Mm-hmm.
So where is it possible to have those electric fields cancel out?
Mm-hmm.
So is one,
Um,
2, 3, or 1 and 3?
1 and 3
1
because
and
they
3.
both go opposite directions.
So there, that's your answer. Okay. All right. So this, by the way, is an exam style question I got from the book I'm using. Is there any is there any one problem we can do again? Okay, I can't find a simple enough one for now. Right. So we'll just end it right there for Coulomb law and electric fields. Okay. All right. So on Sunday, what we'll do again, we'll review a little bit on mechanics, especially this bit about resolving forces. Okay.
Mm.
All right. So any other questions?
That's it. I was just confused of the arrows, but like
Mhm.
I think the arrows only determine or only important if I look at it from the view of like where the point I'm talking about.
Mhm. Now also it matters whether you're talking about forces or electric fields. Okay. So the
Yes.
way you would draw the arrow would depend on whether it's an electric field or a force. If it's a force, you just draw the single arrow. And it's
But if
always
it's electric field,
if
both ways,
yeah, in electric fields both ways depending on whether it's inwards or outwards,
positive and negative. Yes.
positive or negative. Okay. All right.
Mm.
So, anything else you'd like to say? I think.
I think that's it.
All right. So we can end it here then. So I'll see you on Sunday.
Okay.
All right.
Thank you.
Okay. Bye bye now.
See you. Bye bye.
Okay. So that's the end of that lesson there. Um, hope for anyone who sees this or is currently watching, hope you see this very useful or you find this very useful. And okay, I'm also logging out. So see you